flights a year in order to simply keep those people employed and not have a gap. Okay? The purpose of having a human spaceflight program is to actually accomplish something. And while it was questionable to have a shuttle program that flies 4 shuttle flights a year for a budget of $5 or $6 billion a year, it's 4 times as questionable to have it budgeted at the same amount that flies 1 flight a year, and infinitely more questionable to have it budgeted at that rate flying no flights a year. So that's not the issue. The issue is, are we going to spend another decade of zero accomplishment in human spaceflight? Are we going to spend another decade where if we have a conference and people go back and look at it, they say, how far ahead are we from where we were in 2010? And the answer is nil. Just as we can now say, looking at the year 2000, and say nil. Okay? Because the Bush administration, while announcing a push towards the moon in 2004, said, yeah, and you can start working on it after we leave office in 2009. And I met with Mike Griffin in 2005, and I said, look, you can't do this. All bets are off on January 21st, 2009. You need to just fly 1 more shuttle mission, repair Hubble, shut the thing down, move the money over into funding serious development of these lunar systems so this thing is well on the way by the time you are kicked out of here the day after the inauguration. And the didn't do it. Now, there were various constraints on him. There were other people. Okay, it wasn't all up to him, but nevertheless, it didn't happen, and the predicted result occurred. Okay, if you want to go to Mars, okay, let's be clear about this. If you want to go to Mars, you cannot do it in 30 years. You can't do it in 20 years. You've got to do it in 10 years or less, or you're guaranteeing that the political decision that allowed you to launch the program will be voided before you do it. Okay, Okay, so, this was Bush's rope sail, which is fortunately off the table. Now, this is the current rope sail, which is the electric propulsion. And the claim that we can't go to Mars unless we have much faster propulsion, and that electric propulsion is the way to achieve this. Now, both of these propositions are false. Okay, we can go to Mars at current rates. The radiation doses that would be received on going to Mars on 6-month transfers, which is what is possible with current chemical propulsion, are less than what has been received by a number of astronauts and cosmonauts already on the space station program, and no radiological health effects have been observed among that group of about half a dozen people, nor would any be expected based on our extensive knowledge of radiation health effects. But furthermore, there is no prospect whatsoever of nuclear electric propulsion achieving fast transfers. In order to do that, they would need to have power to mass ratios at least about 100 times better than what has actually been achieved, and power levels 20,000 times bigger than what has ever been achieved in space nuclear power systems. The numbers here, the reality, by the way, that I'm quoting here is not actual reality. It's what the Prometheus program hoped to achieve in its program. The actual reality is not 65 kilograms per kilowatt, but 100, which was achieved with Topaz, although that does not include the weight of the electric thrusters, which would be an additional 20 kilograms per kilowatt. But even so, using Prometheus numbers, you're talking about 4-year transfers to Mars, as opposed to or 6 months, which can be done readily with chemical or nuclear thermal propulsion. Okay, so they're going to test an electric thruster on the space station and say, see, we have achieved a milestone. Well, actually, it's known that electric thrusters work, and testing it on a space station will be a nice thing to show, but fundamentally the issue is the power source. And you know, Franklin Chang Diaz says, my Vasimir can get you to Mars in 40 days, provided I have a 200,000 kilowatt power supply. And the largest power supply that's ever been flown in space is 75 kilowatts. Okay, there's a certain leap there. Anyway. Skip that. All right, so what do you really need if you want to go to Mars? Okay, you need a heavy lift booster. Okay, that's also what you need to go to the moon or a near-Earth asteroid. There's any number of designs for a heavy lift booster. The Ares 5 would have worked. This was our own design in Mars Direct, a shuttle-derived heavy lift booster. Frankly, you could use a Saturn V. You could use an Energia derivative. It's not rocket science. Okay. And you use the upper stage of the booster. See, if you get away from this vision of constructing Battlestar Galactica spaceships, okay, serviced on orbit by orbiting propellant depots, and there's more that could be said about that. The orbital propellant depots, okay, they have to be in at least a 400-kilometer orbit in order not to re-enter. They have to be in a 1,000-kilometer orbit if they're going to service a nuclear-powered Vasimir, which would greatly reduce the lift capability of the boosters that are delivering payloads to the propellant depot. And then the propellants are stored on orbit for extended periods of time in heavily insulated tanks. Do you transfer the tanks or do you transfer the propellant? If you transfer the tanks, then you're transferring heavy tanks to your flight vehicle. If you transfer the propellant, there's various technical issues associated with doing zero-gravity cryogenic propellant transfer, but beyond that, you have to have a complete set of tanks on the flight vehicle, which means you still need a large fairing launch vehicle. I mean, it just gets worse and worse the more you look at it. On the other hand, if you just have a heavy lift booster with a good throw stage, and you design your Mars mission around the idea of discrete packages that can be thrown to Mars, lift and throw, using the capacity of the available launch system, which after all is how the robotic system progresses. We have this launch vehicle with this transfer stage, and so the package has got to be this big. Then you can do a manned mission. And so we come to the Mars Direct plan. Okay, launch a booster, use it to throw an automated payload on a minimum energy trajectory to Mars, aerobrakes at Mars, lands on the surface. On the Mars Direct plan, what that payload is the Earth return vehicle, which flies out to Mars unfueled. It has with it, not shown in this diagram, a nuclear power reactor, about 100 kilowatts, mounted on a rover, so it can be driven a couple of hundred yards away from the Earth return vehicle, put down on the ground. It can deliver power to the ship. The ship brings to Mars with it, in some of its unfueled methane tanks, about 6 tons of liquid hydrogen. The liquid hydrogen can be reacted with carbon dioxide, which comes from Mars. The Martian atmosphere is 95% CO2. We can acquire it by running a roughing pump. You will react the hydrogen with the CO2. With a ruthenium on alumina catalyst, you can produce methane and water. This is known as a Sabatier reaction. It's been practiced in the chemical industry since the gaslight era. The methane is stored. That is excellent rocket fuel. The water is electrolyzed. Once again, 19th century chemistry. Split it into hydrogen and oxygen. The oxygen is stored. That's your oxidizer. The hydrogen is recycled to make more methane and so forth. And then you run a third reaction in which you just break down carbon dioxide into carbon monoxide and oxygen. The oxygen is stored as useful oxidizer. The carbon monoxide is released as waste. You can do that on Mars. There is no EPA there yet. When all is said and done, you can take 6 tons of hydrogen from Earth and turn it into 108 tons of methane oxygen bipropellant on the surface of Mars. It's a very large leverage, 18 to 1, and it allows you both to fuel up the Earth return vehicle as well as having an excess supply that you can use to power ground vehicles using chemical engines, which is a tremendous advantage. They have much higher power to mass ratios than you can get with electric vehicles. That's why they're much more popular on Earth, as you may observe if you go outside. And and on Mars, in a frontier environment where you really do need the long range and the torque and the hauling capability and the all-around muscle you have from having a real car instead of a golf cart, you really want to do that. And of course, mobility is the key requirement for exploration. And so this is very important. In other words, the ability to make propellants on Mars is not just the key to making the mission cheap. It is also the key to making the mission effective, which is equally important, because there's no point going to Mars unless you can do something effective once you get there. And mobility is the key requirement for an effective human Mars mission. Okay, this technology, well, this is one that we built back in '93. This is full scale for a Mars sample return mission application. But actually, there was really nothing new here. We were just building this to prove to NASA managers that chemistry was true. Okay, now, okay, so it took 8 months for this to fly to Mars. It took about 10 months to make the propellant. That's 18 months. It's 26 months in between launch windows from Earth to Mars. So long before the next launch window opens up, we know that we have a fully fueled Earth return vehicle waiting for us on the Martian surface. That being the case, in the next launch window, we launch 2 more boosters off the Cape. One shoots to Mars, another Earth return vehicle package. The other shoots a habitat with a crew of 4 astronauts in it. Now, the habitat could be a simple tuna can design, similar to the ones that we have at the Arctic Station and the Desert Station. 2 decks, each with 8 feet of headroom. And here's one layout of an upper deck of the Hab. There's any number of layouts you can use. One thing that's shown here is, though, in the center is the solar flare storm shelter. This circular thing. There's 2 kinds of radiation that can get you in interplanetary space: the solar flares, the cosmic rays. Solar flares are intense events. You can get thousands of REMs in the course of several hours, which is enough to kill. However, it's only protons with energies on the order of millions of volts, and that kind of stuff can be stopped by 5 inches of water, or things that from the nuclear point of view are essentially the same thing as water, such as food, or things that water and food become as the mission proceeds. And we have enough of that on board a Mars mission simply by virtue of the fact that it is a long mission to provide shielding to that thickness if you basically create your pantry as your storm shelter. The other kind of radiation that gets a lot of talk are the cosmic rays. Now, and this has been greatly mystified. And it's very unfortunate. It's been mystified by people who are pushing advanced propulsion, who want to insist that we must have radical new propulsions before we can go to Mars. Once again, you can't do your program before you do my program, by radiation researchers, and also by people who just don't want to go to Mars. But it's just false, okay? The amount of cosmic radiation in interplanetary space, and it varies somewhat between solar max and solar min, but you're talking about 50 REMs for every year you're in interplanetary space, and will be in space for a year on a Mars mission. 6 months out, 6 months back. You'll be on Mars for a year and a half, but there we have all the shielding material we could possibly want. We could put sandbags on the roof of the Hab. We can do all kinds of stuff. Now, these are the doses that have been received, and actually full, since this chart was made, is now up there at over 100 REM, by various cosmonauts and a couple of our astronauts due to space station activity. The cosmic ray dose rate at the International Space Station is half of that in interplanetary space. The Earth's magnetic field does shield out solar flares. It does not shield cosmic rays. Okay? The thing that protects you from cosmic rays is not the Earth's magnetic field, it's the Earth's atmosphere.